So if you go on Blackboard, you'll see I posted a few more Desmos links related to the law of sines and cosines. I'm going to explain how they work in a couple of minutes, but wanted to kind of at least get the setup here. All right. So in this instance, we have triangle AB. Well, solve each triangle. I guess that's a typo. Each triangle refers to triangle ABC, but there's no indication of that. All right. So given triangle ABC, solve each triangle and then find the area where applicable. Oh yeah, well, I guess that makes sense. Well, you'll see in a couple minutes. So triangle ABC, oops, my iPad moved on me. With corresponding sides, lowercase a, lowercase b, lowercase c. All right. My lowercase c looks about the same size as my uppercase c, so I'll make it a little smaller. So angle A is 42 degrees. I'm going to bring it in here. 42 degrees. Side A is 22. Side B is 12. Okay. So depending on the arrangement of information that you're given, it dictates which type of technique you should use, law of sines or law of cosines, because A is bothering me. So if you have a triangle where the information that's either presented or requested is in the form of angle, angle, side, angle, side, angle, well, angle, angle, side, or angle, side, angle, you're going to use the law of sines. If you have angle, side, side, angle, side, or side, angle, side, you're going to use the law of cosines. All right. So that leaves other situations, but I'll get to those in a minute. But first, I want to really talk about what it means to be angle, side, side. I'm sorry, angle, side, side. That's what we have here. Angle, angle, side, or angle, side, angle, and all that stuff. All right. So just kind of off on the side, I suppose, I'll just draw a couple of quick diagrams. I wonder, I can probably steal the space for number 4 and just draw the diagrams there. So, because we're not going to do number 4 anytime soon anyway, so I could always just kind of move it later on. So just ignore 4 for now. But angle, angle, side. What that means is that you're given a triangle and you know an angle, another angle, and a side that's not included in between those two angles. All right. So a format of something like that would be along these lines. So you would know an angle, another angle, but then the side that you know would not be in between the two angles. So here's one angle, here's another angle. This side would be in between those two angles. I'm saying not that side. The side that you know or you're looking for is one of the remaining sides. So for example, this one, right? So that's an example of angle, angle, side. Right? There's other possible ways that you could have an arrangement. I mean, you could diagram out every possible arrangement of two sides and an angle, where the angle where the side is not in between the two angles. I could do that all day long. I can go. I mean, it's a lot to draw. You don't want to get into that. But let's say I know these two angles, and perhaps I know this side, right? So I know two angles, and the side that I know is not included in between those two angles, right? Another possibility would be if I took pretty much the same setup here, but instead of having this this side be the known side, maybe I know this side. All right. Same idea for this one. Maybe I know, instead of this side, maybe I know this side. All right, so it tends to be a lot because there's every possible variation has, you got to consider. But if you know an example of what one instance of angle side looks like, then you can kind of reason out what all the remaining possibilities would look like. All right. So then, like I said, I mean, you can place your angles and sides wherever it makes sense. And so, yeah, then I guess the one additional possibility would be maybe you know this angle and this angle, in which case you might identify this as the remaining or the non-included side. Right, or maybe it's this one. Right. The reason why this is important is because it's going to help us identify what the most appropriate approach is, whether it's law of sines or law of cosines. Right. So if you know two angles and you know a side, you're typically going to be using the law of sines. But it's even better than that. Right. And that has to do with what I posted on Blackboard. I have separate Desmos links for you, all based off of whether you know your arrangement is angle, angle, side, angle, side, angle, side, 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 angle, side. So having an idea of what the different arrangements are, that would be pretty important, right? Otherwise, you'd be just kind of guessing and checking. It would be sort of, not ideal. Let's just put it that way, right? So I'll take you through the other possibilities. We have angle, side, angle. I'll just give one example though, because if we do 6 examples for each one, it'd be here for the rest of the night doing it. Right? Although, I mean, I like drawing triangles, so it's fine. All right. So Miguel, I got you for attendance. You're all good. Or at least I'm about to get you for attendance, so you will be all good. I've officially gotten you for attendance, so now you're officially all good. All right. So angle, side, angle would be the instance, or an example of angle, side, angle would be knowing two angles, but now the side that you know or are looking for is included between those two angles. All right, so this would be an example of angle, side, angle. All right, side, side, side. Well, actually, what did I do? What did I say next? Side, side, side. That's actually the easiest one to identify, because all that is an instance, and actually there's only really one way to represent this. This would be an instance where you know 3 sides of a triangle, but you don't know anything about the angles, right? And then side, angle, side. Side, angle, side would be the instance where you know 2 sides and the angle that you know is included in between those 2 sides. All right. So for example, I know this side, and let's say I know this angle. All right, that angle is included between those 2 sides. You can't get, as you're going around the triangle, you can't get one from one side to another without passing through that angle. Right, you just kind of think of it as a pathway. You're actually physically standing on the perimeter of the triangle. If I were to start here at this location and travel around the perimeter of the triangle to my other known side, the angle that was included in that journey, the angle that I would have to pass through, the turning angle, that would be the angle in the SAS. All right. So there's other possibilities, but these are generally the ones that we focus on, right? At least to get started. And then now as I look at it, I realize that number 1 is actually not one of those, because that's the case of angle, side, side. which is known as the ambiguous case. So actually, let me come back to that one in a little bit. But let me just make sure that I have one that is going to be good to go. No, it just occurs to me that they're all ambiguous. All right. Well, that kind of stinks. Well, you know what I'm going to do is I'm going to do what I always do in a situation like this. I'm just going to make up an example. All right. So, of course, I put stars on the ones that you wouldn't be able to do. I apologize for that. It's terrible. Unforgivable. ABC. Let me do I'm going to look at number 5, but I'm going to modify it. I'm just going to move some things around. All right, but it's going to be triangle ABC because the numbers are kind of nice, but it's not quite the way we want it. All right, so I'm going to say instead of side C, I'm going to say that that's side A. All right, so I'm making a change to number 5. Sounds like a delivery. All right. And let me just bring this stuff down here so I can point to it. This went off the rails pretty quickly and easily. All right, so let's say you have this arrangement of values. Side B is 15. All right, so B is 15. Side A is 13. And the angle included between the two is 50 degrees. All right. This follows the format of SAS because what I know is a side. So this is a side that I know. This is an angle. Right here is an angle. And this is another side. All right. Because it's in that arrangement, it's a SAS situation. We would use the law of cosines to figure out all the remaining bits and pieces. All right. So let me show you the Desmos links that I created because that's going to actually do all the work for you so that we could jump into the applications questions. And then I'll figure out a better set of examples for you to work on because this was not what I had in mind. Honestly, I thought I edited these. Well, that's usually what my excuse is. But apparently I didn't. So here we are. Let me just get rid of this. So let me just pause the recording real quick. Resume recording. Under calculators, unit 3, we have all these different options. We have unit circle. That's a fun one. But law of sines and cosines, SAS, law of cosines, SSS, law of sines, AAS, and so on. But the bottom line is, I mean, whether it's his law of sines and cosines, law of cosines, law of sines, it doesn't make a difference as much as we care about the SAS versus SSS versus AAS and ASA. All right, so for this instance, we would select this calculator, which has a triangle built, just for reference. And then it has some sliders and some instructions. All right. So I'm going to open that up on my screen here and then come back. All right. So law of making sure I'm opening the right one. Okay. So pause the. All right. All right. Well, we'll get the solution in a minute, but thank you for mentioning that. All right. At least we can get it from here on out. I'll just fill in the gap later on. All right. So what I would do here is I would just draw a bare bones version of this triangle. All right, without all the bells and whistles. All right. So I'd label it ABC. We know, well, it says 2 degrees off of the vertical, but there's also a 90-degree angle here. All right, so this is 90 degrees. We got 90 degrees combined with another 2 degrees, gives me 92 degrees. All right, this one they told us just flat out is 45 degrees. And then they told us the length of the side contained between those two angles. All right, so they gave us an angle, a side, and an angle. All right, they gave us an angle, a side, and an angle, an ASA situation. Right, now they are asking for the length of the lamppost. You know, it's leaning, but they're asking for that length, and that would be this side here. But if we solve the triangle, then we'll get what we need anyway. Right, so you go on the blackboard, you look at your law of sines and cosines, you find the one that says ASA. Just make sure that the information is organized the same way your diagram is organized. Now, the triangle shape may not be identical. That's fine, as long as the information is placed on your triangle the same way as it's placed in the example triangle. ABC, starting in the lower left-hand corner, working its way around counterclockwise. All right, so we know side C here. I need side B, and here's side A. All right, now they're not asking us for side A, but you know, if we can get that information, that'll be great. It's just more information. All right, they are in fact asking us just for side B. So once we come up with that, we've actually answered the question. All right, but this will give you everything. All right, so given a triangle with two angles and an included side, for example, knowing ACB. All right, so that's angle A, side C, angle B. That happens to be what we have. All right. If not, then you would reorganize your labeling or your triangle to make it fit that structure. All right. So angle A is 92. Gotta get it on that 92. If not, you just, oh, I had it and I lost it. Okay. B is 45. We're good there. And C is 25. All right. My slider only goes up to 5. So I'm going to tap on that and pop into 2. So I have my information here. It says law of sines will solve for the missing sides. Well, yeah, but before we do that, it's, you know, just simple arithmetic. It's going to give us angle C. So I might as well just pop that in there. That's 43 degrees. All right. A, just using a similar justification for what I talked about over here with the law of sines, the idea that if you choose the appropriate pairs of ratios and set them equal to one another, then you can cross multiply, simplify, and solve, and come up with a rule to solve for a side or a missing side or a missing angle. That's the rule that's plugged into Desmos. So A is equal to C sine A over the sine of C. So A is equal to C, which is 25. That's the side C. Sine of angle A, which is 92 degrees, over sine of C, sine of 43 degrees. Right? And that's going to give you approximately 36.6 as a result. All right, so that's side A. All right, they didn't ask for that, but you know, you can see how you might be presented with a situation where you'd need to know that. All right. Now, and for example, this lamppost is falling over, or it seems to be anyway. It's only 2 degrees off. It's a kind of an exaggeration. But what if they said that in order to keep the lamppost from falling over, they had to tie it down with a cable? How long would the cable have to be? We would have just figured that out. All right. So it is still useful information, just not for this particular question. All right. So to find side B, we would have to compute C sine B over sine C. All right, that's what you would get. And you could try this if you want. That's what you would get if you took the sine of, oh, wow, I don't even know how I missed that. That's supposed to be sine of B over B. This is what you would get if you took sine of B over B equals sine of C over C and solved it for just the B. All right, cross multiply and solve. All right. So this would be, you just pop it in your information, 25 sine 92 over sine of, let's double check here. Yes, okay. So over sine of 40, so the B value is what I needed on the top of, so this would be 45. I knew I fell into a trap there. So this is 45 degrees, that's angle B over the sine of 43. All right. So B is approximately 25.9. So that's this side. So B is approximately 25.9. So now we have the solution to the triangle. Right? We know all the missing sides and angles. They said find the length of the lamppost. The lamp to the nearest tenth of a foot, the lamppost is 25.9 feet. All right. So we'll come back to number 2 because that's another angle side situation. But looking at number 3. Number 3 is a situation that's, again, another fairly clean one based off of the diagrams we were drawing before. But you could see that even though it's a lovely picture, it's a little bit too lovely, right? So I'm going to draw a bare bones version of this without all the bells and whistles. And just kind of get that out and look at that separately. I'm going to call that ABC. All right, same orientation, just slightly different in terms of the sizing. All right, so I know I have 120 here. I got a 23 here and 110 here. All right, so I know an angle, a side, and an angle again. All right, so an angle, another angle, but the side is included in between those two angles. All right, so even though we're looking at a triangle that looks wildly different from the previous one, it's still the same structure, and we can get all the information that we need just based off of the same desmos. All right, so it's saying to the nearest tenth of a meter, find the height of the tree. They're asking us for side A in this instance. All right, now this process is going to give us both sides A and side C. Side A and B, but we only need the side A. Right, so I would toggle my sliders to the appropriate values. A goes to 23. B goes to 110. And C is 120. I got to type that in. All right. So knowing that, the angle C we could have figured out just by subtraction, but it's going to do it for us, so why not use it? So 47 degrees, right? So A is equal to C sine A over sine C. And you know what? I know I did this before, but this is when when I forgot to unpause the recording. Let me just show you again really quickly how we would come up with this formula. So we have the sine of A over A. We have the sine of B over B. And we have the sine of C over C. All right. The law of sines. Now, in this scenario, I'm looking for side A. Right? That's the height of the tree. So I would want the ratio that incorporates side A. Right? I know information about side C, so and angle C. So I'd want to have that involved in my computation also. Right? So in theory, you could just do this, you could crank it out by hand, but I have the Desmos set up to do it for you. But what Desmos is doing is taking your sine A over A and setting equal to sine of C over C, cross multiplying and solving that for the value of lowercase a. Right. So, and you might remember this from previous math classes, but maybe not. I don't know. Memory's a thing. And also, I mean, you never know, like who's tuned in at what moment. But memory is the word of the day, by the way. Yeah, the issue is that like even if it was something that you would know, you don't necessarily are always going to remember it anyway. Right? But that being said, preamble aside, if you have a proportion, the diagonal values are what I call groupable, but they're also interchangeable. All right. So that means that I could take any value that's along a diagonal in a proportion and swap it, group it together, however I want to organize it. Right. So what I can do here is I could take, and this would have saved us a little time earlier, but I didn't do it. So here we are. So I can take these two values and swap them. So then it becomes sine A over sine C is equal to A over C. All right. Then I can just move that C up to the top part of the other fraction because, like I said, the diagonals are groupable, which means that I can take them and put them together. It's just a question of put them together where. I can put them together anywhere along the diagonal. I can put them together in the upper left-hand corner, so in the numerator of the first fraction, or the lower right-hand corner, which would be the denominator of the second fraction. The long story short, I can take this C and just send it on up here. Right? So that would give me this rule. Right? Then in that rule, I would replace the C value, the side C with 120, because that's what side C is. Sine of angle A, which is 23 degrees, over the sine of angle C, which is 47 degrees. And that would give me A equal to 64.1. It said to the nearest tenth, find the nearest tenth of a meter, find the height of the tree. So 64.1 meters. In the first problem, I found the other side just to show you, but in this case, I couldn't come up with a real justification for doing that. Like I don't know why I would want to know the length of the dotted line or dashed line. So I figured, why bother? But at a minimum, you get a little review of, it's called the product of the means equals the product of the extremes, the old geometry rule. In fact, most of the issues that people have in this topic really doesn't have anything to do with trig or algebra. It has everything to do with gaps in content knowledge related to geometry. And most of the time it's through no fault of their own or your own. It's because geometry is kind of like an unofficial, I hesitate to say the word prerequisite because it's not a prerequisite for this course, but it's kind of like an expectation. Like, well, of course they all know geometry, or at least enough geometry to be successful here. So, but then, usually what ends up happening is that's not the case. And so things like when I say SAS, ASA, SSS, like in theory, you're supposed to have already seen that, but I, for the life of me, could never figure out what part of the curriculum you would have seen that in what course. Definitely not in the pre-algebra, beginning algebra courses, college algebra. If you took a geometry class, then yeah, definitely, but that's not a requirement. But somehow they expect that you have some sort of experience with that. Right? But I go over it because I can't rely on that. So anyway, let's go back to number 2 real quick. So this says a derrick at the edge of a dock has an arm 25 meters long that makes a 122-degree angle with the floor of the dock. The arm is to be braced with a cable 40 meters long from the end of the arm back to the dock. Right. The nearest tenth of a meter, how far from the edge of the dock will the cable be fastened? All right. So whether you know what the hell a derrick is, honestly, I don't even know. I'm assuming it's like this boom thing, but I've never been 100% sure. I've been using this same worksheet for like 20 years too. But the part where it says how far from the edge of the dock will the cable be fastened? All right, well, that part's easy enough. I mean, it seems to be the case that they're asking for this length. All right, so this is some unknown length that we have to figure out. All right, I mean, this seems to be the cable. I'm guessing this is the dock, this whole structure. This looks like some sort of fastening or a tie down, so it's probably what they're looking for. I can tell you on a test that I tend not to go into the realm of things that are too much in the niche category. So, or niche. Apparently, you could pronounce that word either way. I had no idea. Pronouncing a niche for like my entire life too. So anyway, again, we have another situation where beautiful looking diagram, but a little too beautiful. So let's kind of trim this down and make it a little uglier. Nah, it still looks gorgeous. It's just, we don't need all the bells and whistles, right? So again, we label it ABC, working from the lower left-hand corner around in a counterclockwise fashion. All right, we know, I mean, it's hard to see, but this is a measure of the arc of the angle, and they're saying that that's 122 degrees. This is 40 meters. All right, so that's going to be side A. And then this one, side B, is equal to 25 meters. So I need to figure out what side C is. All right. So this is kind of an interesting situation. Maybe you don't realize it yet, but you will in a second, especially when I point it out. All right. You know two sides and you know an angle. All right. But that angle is not included in between the two sides. So this is not an SAS situation. All right. In fact, it's an angle side-side situation. All right. Or a side-side angle if you don't want to be like inappropriate, I guess. But what we need to do is use the law of sines to come up with an angle. And then from that angle, it's a two-step process. We need to then discover what the missing side is. All right. So we have to use the law of sines twice here. right? And the problem is, it's what's known as the ambiguous case, because there's multiple solutions when it comes to an ambiguous case, even though a lot of them don't make sense geometrically, in this particular context. Desmos has a hard time with it. So there's no Desmos app for this, right? We have to just grin and bear it, I guess. So we're going to look at the sine of A over A is equal to the sine of B over B is equal to the sine of C over C. All right. We look at what we have. I know angle A and side A. So I definitely want the ratio that involves those two metrics. The only other piece of information that I know is side B. So I'm going to grab this one. So I'm going to say the sine of A over A is equal to the sine of B over B. I'm going to solve that. Well, the only thing I can solve it for is B. So I'm going to use a little hocus pocus here. Remember that the product of the means, or the groupable diagonals and diagonal swapping and all that good stuff. But basically what I'm going to do is I'm going to take this B, save myself some time and energy, and just send it up there with the sine of A. So we would say sine of B is equal to B sine A over A. All right. Then, and I'm just going to get a fresh new Desmos here in degree mode. Then I'm going to find the arc sine of both sides. So B would be equal to the arc sine, or the inverse sine. Remember, they mean the same thing, of B sine A over A. All right. So I know my B, I know my A, I know all that information. I can just pop it in here. So arc sine 25 sine 122 over 40. So that's what I'm going to pop into Desmos. Arc sine fraction sine. So function, trig, sine. You can type in the word sine too. 122, just make sure you're in degree mode, over 40. And then let me just show you really quickly, because I've been saying this a bunch of times, but I haven't really backed it up, at least this class. If I've been saying that arc sine and inverse sine mean the same thing. So let me just justify that real quick. So if I did inverse sine 122, 25 sine 122 over 40, you see I get the same value. All right. They mean the same thing. All right. Bottom line is, I now know angle B. Angle B is equal to 32-ish. Right. So it's this disgusting decimal. Right. So 32.007485, blah, blah, blah. All right. But what I'm going to do is I'm going to use my Desmos here to my advantage. I'm going to call this capital B. Capital B is equal to that. And I'm going to get rid of the second one because I don't really. Right. But now anytime I look at the capital B in Desmos, it's going to bring up that number. All right. So I don't have to worry about retyping that value. I saved it as really its proper name, which is angle B. So what I need to do now is use that to help me figure out a couple of other pieces of information. Well, ultimately, I need side C. If I know that angle B is approximately 32 degrees, then angle C is going to be 180 minus my known A value, which is 122, minus my known B value, which I don't want to get into typing that whole decimal in there. All right, so I just type in the B. So that's approximately 26 degrees. But I'm going to call that C now, capital C for side C. All right, so now anytime I reference a side C, I'm sorry, an angle C, I said side C like twice. Anytime I reference an angle C, it's going to bring up the 25.9 blah, blah, blah. All right. So now, so I got this whole string of stuff here. And you know at this point that you could submit your Desmos work. So if you do everything like this on Desmos, you don't have to then rewrite it on paper. You know, so that's an important piece. All right. Let me just move this over here and continue with this up here. All right. So now I need to know how to, well, I got to figure out side C. All right. So I need to know how to manipulate my law of sines in order to pull that off. So I go back to my law of sines and I'm looking at it and I'm saying, all right, well, I knew everything there was to know about angle A and side A. So I'm going to hang on to that. That's good information. But now I need to figure out what side C is. So I need the proportion that involves side C. So I need this proportion. So sine A over A is equal to sine C over C. And for this one, I said C. I don't know why I wrote an A. But for this one, I'm just solving for the C. So I'm going to do my diagonal grouping and swapping. And in doing so, I'm going to take these two and do a switcherooski. That's going to give me C over A. Well, let me just keep the color coding. C over A is equal to sine of C over sine of A. If I want C alone, now all I would need to do is just send that A up to the numerator of the other fraction. So C is going to be equal to A sine C over the sine of A. Keep my color code. Right. So now I have the relation that gets me side C. All right, so now I just got to plug some numbers in. All right. So I know that side A is 40. So C is going to be equal to 40 sine, well, angle C was approximately 26. Angle A was an exact 122. That's what they told us. So what I would do at this point to figure out side C is just pop this in, but I'm going to use a capital C instead of typing in the 26. All right, so 40 sine capital C over sine 122. All right, and again, just make sure you're in degree mode and you'll get the appropriate results. All right, so we're talking about 20.7. Nearest tenth of a meter. And that would be the most exact answer that we could get because we worked with exact values along the way. but that's obviously in contextual situations the most complicated situation, right? That's the angle side psi, right? Just going back to what they gave us initially, they told us this piece of information, this piece of information, and this piece of information, right? That was an angle, a side, and a side, but the angle was not contained between the two sides like it would be for SAS, right? So that made things a lot more complicated. Or interesting, depending on how you look at it. Right, but at long last, we're done with trig. Honestly, you're never going to be done with trig. I mean, assuming you have more math to take after this class. If you don't, then you will be done with trig. But if you have more math to go after this, it's just all trig all the time. So starting with the unit circle, getting to understand those identities and all that good stuff. But at this point, we can actually take a little break from trig and talk about something called conic sections. But I can tell you that conic sections are actually best understood through a trigonometric lens, meaning we're gonna work with variables in terms of x and y's, functiony looking expressions and equations, even though they won't be functions in terms of what we're accustomed to. But they really should be represented in terms of things like sines and cosines, right? But we got to start somewhere. And so we're going to go into the world of conic sections. And conic sections are kind of a weird term, right? Because it's like conic sections, like section of like the textbook, like the course. Like, what are we talking about? Actually, if you were, and what you see in these diagrams are actually what's being described. If you were to take a cone and an inverted cone and put them end to end, and then think about all the different ways you could slice through them, you would end up with what we call conic sections, right? If you do it in an oblique fashion, you get your classic parabola, but that parabola could have a variety of different orientations. If you slice through a cone horizontally, you'd end up with a circle. If you do it in an oblique fashion, but you do it such that it goes through the surface of the cone, not the base, then you'd end up with an ellipse, so a little stretched out circle. And if you go vertically through it, or at least in such a way that it intersects with the two bases, you'd end up with what are known as a hyperbola. Right? So it really gets at three-dimensional, or it's like the first indication of how we start to evaluate three-dimensional surfaces by understanding their cross sections in 2 dimensions. Right? Honestly, this isn't going to make anybody feel better, but I really feel like this topic is completely and totally misplaced by being present in this course. But it's part of the curriculum, and yeah, so we got to cover it. It's not crazy, but it's another instance in this course where you're looking at a topic that doesn't seem to really overly fit with everything else that we've been working on, right? So it is what it is, but we'll have to just kind of grin and bear it. There is a do now problem here, of kind of a rarity. Not really anything that I'm going to expect you to do on your own. It's just that it's more like a review problem. And what I mean by review is it's something that we've been tabling for a while, right? When we talked about polynomials months ago, really at this point, we talked about solving quadratics. And when we solved quadratics, we solved using factoring and quadratic formula, but we glossed over a really important concept known as completing the square, right? And I said at that time that we would come back to it and it would be really important, right? And I wasn't kidding. It's a very important topic. It's a very important algebraic skill that you're going to need to have conceptually mastered moving forward. It's something that should have been covered last semester. But again, just like I say about everything else, just because it was covered doesn't mean it was absorbed. Right? So I'm going to go over it again, and then I'm going to emphasize again its importance and talk about why it's necessary. All right. So here we go. Solve the following quadratic by completing the square. Now, if I were to solve this quadratic, it's like quadratic. What does this have to do with trig? It's so crazy how this material works. It's like I think it's Tokyo Drift. I've actually never watched any of the Fast and Furious movies.
I so much prefer quadratics to trig.
That's a typical reaction. But I kind of look at it like if you're reading a book or watching a series of movies, and you're like maybe 2 books in or 2 movies in, and then the third movie is like a prequel. And then, but it's not the kind of prequel that you can just skip over and ignore. It's the one that you'd have to watch in order to understand the next movie in the series or the next book in the series. That's what this whole concept of conic sections really comes down to. Right? It's going to seem like we're going out of bounds and we're kind of detouring, but we're actually detouring to, like we're getting off the back roads. We're taking a detour, and because of that, we're going to get on like a major highway, and that's when things start to open up, right? But if I needed to solve this quadratic with Desmos, for example, I might just graph it. Y equals 2x squared minus 4x plus 1, and then just see where it crosses the x-axis. But this is an answer or a set of answers that tells me, okay, it's probably a quadratic formula situation, right? But you could also use a technique called completing the square. So in the technique of completing the square, and I'll just kind of keep a running list of the steps off on the side. There's a bunch of different ways to complete the square. It's unfortunate, but the way that you probably practiced and mastered is almost always this is going to sting, the least useful way moving forward. So the way that I'm going to show you is going to be similar enough that it should seem familiar, but it's going to have some little differences that frankly you may not even like. You may not even like the concept to begin with, but you just got to bear with me on this. All right. So the first thing you do is given an equation in the form of ax squared plus bx plus c equals 0, you move the c value to the right-hand side, RHS for right-hand side. All right. Now you don't just move it. You have to move it using like legitimate algebraic techniques and processes and principles, which in many cases means subtraction, some cases means addition. But bottom line is, whatever my c value is, that's got to get out of it. So I'd have 2x squared minus 4x, but then I'm going to leave a little blank. All right, so that's kind of new. I'm going to leave a little blank and set it equal to -1. So I subtracted the 1 from both sides. So I move the C value to the right-hand side, but I also leave a little blank, right? Because that's where I'm going to complete the square, right? When we say the square, it's really shorthand. It's a lot of sources of confusion come from just kind of skimping on the name of the topic. So when we say complete the square, it's completing the perfect square trinomial, right? So I want a perfect square trinomial, which means a 3-termed algebraic expression, but it's got to be a perfect square, right? So in order to do that, I'm going to compute b squared over 4a and add to both sides. And I never give myself room. Compute b squared over 4a and add it to both sides. All right. So remember, in a quadratic, if it's in the general form, it's ax squared plus bx plus c, whatever the coefficient is of x squared, that's going to be your a value. No, it's terrible. It looks a little bit better. And so that's my a value, my b value. And then the 1 was the c value. We already took care of that. So I'm going to compute just somewhere off on the side. I'm going to compute b squared over 4a. B squared divided by 4a, which is going to be -4 squared over 4 times 2. All right. So that's going to give me a 16 on the top and 8 on the bottom, result of 2. All right. So this is just side computation. All right. Side work. I'm going to take that 2 and I'm going to add it to both sides of the equation. All right. The next step is to factor out the a value. Whatever the a value is on the left-hand side, factor it out. Factor out the a value from the left-hand side and simplify the right-hand side. All right, LHS left-hand side, RHS right-hand side. All right, it's easier to write that obviously than to, LHS and RHS, as long as you know what I mean. If you don't, make a little key for yourself. That should help. All right. I mean, at least if if you make the key, then when you go to study, you won't be thinking like, where did Lincoln High School and Reagan High School come from? So factor out the a value. Now the a value here is a 2. I'm going to factor it out on the left-hand side, but on the right-hand side, I'm just going to simplify. Now, in a lot of cases, that's going to be pretty easy. Some cases you might have some fractions. It's still not going to be terrible, but you might have to do a little bit more work. So, but in this case, it's just a clean 1. All right. So we got a relatively straightforward situation on our hand. All right. So then when I factor out the 2 on the left-hand side, factoring out a GCF, we divide each term by that GCF, x squared minus 2x plus 1 is what remains. All right. So then what we do is we got to do a couple of things. Ultimately, we have to solve for x, but we're going to divide the a from both sides. Now you might look at this. This is where people start kind of like disagreeing with my technique, and I say, well, tough. I don't know what to tell you. No, yeah. The reason I'm asking you to do it this way is because of what follows. Like we need to do this for ellipses and hyperbolas and stuff like that. So there's a reason for it. But this next step, we're going to divide both sides by the a value. But you might look at this and say, well, I could have done that way earlier in the process, right? So you just got to kind of fight that, right? That's the way you may have seen it in the past. And I'll tell you right now, I've had, it's a battle. I have tutors tell my students over the years, oh, why are you doing it this way? It's so much easier to do it this way. Your teacher is telling you to do it this way. That's wrong. And I'm like, well, that's because your tutor doesn't know the math enough, right? And so they're telling you that something's wrong when it's right. It's so infuriating, right? But I can promise you, this next step, even though you might not like it, I'm not going to go as far as to say it's controversial or anything, but this next step, divide both sides by a, is usually the step people don't like, right? But you got to do it. Both sides by a, right? So I'm just going to show the division, the result of the division. You're going to have x squared minus 2x plus 1 is equal to 1/2, because the 2 will cancel on the left, and you'll have a 1 divided by 2 on the right. All right. Factor the left-hand side. I'm up to blue. All right. So the left-hand side should now be a perfect square trinomial and should therefore be factorable. All right. So in this case, it ends up being x minus 1 times x minus 1, which is really just x minus 1 squared. If you've done every step up until this point correctly, then it should be very easy to see what the factors are here, right? Because your first value should multiply by itself to get this. Your second value should also multiply by itself, but to get this, all right? And if that plays out, then you've done it right. So then you're in the home stretch. You take the square root of both sides. Take the square root of both sides. We're actively taking the square root, so that means we're going to pop a plus or minus on. Ugh. Come on. Yeah, there we go. So on the left-hand side, x minus 1. On the right-hand side, we're just going to say plus or minus the square root of 1/2. Another common misconception. Again, I've mentioned this a few times. I know I have. I know there's plenty of instances where I forget to say things, but this is not one of them. It doesn't matter if you have a radical in the bottom of a fraction. It doesn't matter if you have a fraction inside of a radical. These are all things that are okay. Whenever somebody said that you can't have a radical on the bottom of the fraction, they were full of it. All right. There's absolutely nothing wrong with having a radical in the bottom of a fraction. All right. So we factored the left-hand side. We took the square root of both sides. All right, we can't forget the plus or minus. All right, whenever we take the square root, we're gonna have a plus or minus, but then the last step is just isolate x. All right, so we would do that by adding a 1 to both sides. So x would be equal to 1 plus or minus the square root of 1/2. All right. So 1 minus the square root of 1/2. That's the 0.293. 1 plus the square root of 1/2. Compare that with the roots that Desmos showed. and we have what we're looking for. All right. So if you're familiar with completing the square, then it's a slight, the technique that I'm asking you to use is a slight adjustment from what you've been used to, but it'll pay off for you. All right. If you're not familiar with completing the square, honestly, in this situation, that might be better because then you're kind of a blank slate. You're just following the steps, right? And you're going to kind of see where this goes, but you're not kind of predisposed to do it any other way. You know, like we're all creatures of habit. You know, it's like, which way is the best way? Well, the way that you learned first and the way you're comfortable with. Right? So why do you do it that way? Because that's the way I learned it. Right. So it just kind of is what it is. But yeah, this is the way I'd like you to do it. We're running low on time here, and I don't want to get too far into completing the square of the conic sections. So what I'll do is I'll just throw in another example here, and I'll call that the quote unquote homework. You know, it's not really. I'm going to make it a starred problem, a practice problem that we'll go over next time. So I'll say try. Oh, let me just make sure I picked something that works but isn't too nice. 3x squared minus 4x plus 1 equals 0. Let me just make sure that that's sufficiently nasty, but not too nasty. Oh, of course, it's like the nicest and cleanest one ever. All right, hold that thought.
No, we're good with this.
No, you don't want it to be too good because then you're not going to learn anything from it. It's too easy.
Oh,
So try something new from there.
Yeah, so minus 1 instead of a plus 1. Yeah, because if it ended up being too clear, no, don't get me wrong. I don't want to torture you, but if I gave you something that was too clean, then the whole stuff with the square roots doesn't really become a factor, doesn't become a part of the process, and it lulls people into a false sense of security into thinking that this is a whole lot easier than it really is. Right? So I'd rather you try one that's a little beefier, and then we'll go over that together, and then we can kind of pick up the pieces next class. All right. So yeah, it's never for the purpose of torture. Right? Well, not intentionally.
uh-huh.
So that's where we're going to leave it for